Okay, this is multivariable calculus, and in this video I'm going to talk about section 14.1, which is functions of several variables. And before I jump into this section, I just want to give you a heads up of where we're heading with all of this. So in multivariable calculus, we have really two big units that I would consider to be the bulk of the material that we cover in this course. And this is one of them, partial derivatives. So when we talk about partial derivatives, we're going to start analyzing functions in the same way that we did in 2 dimensions, but now we'll start to look at that in 3 dimensions, and then we'll look at that when we have functions of more variables than 2. So in addition to that, we'll also get into things that we did in 2 dimensions, like we'll look at optimization problems, finding maximum and minimum values of a function, different ways that we can analyze functions using partial derivatives. And then the other big unit that we're going to cover, this is what we'll do a little bit into the second semester. We'll start talking about what we call multiple integrals. And multiple integrals will take us a pretty big bulk of our time in the second semester. That's where we're talking about like double integrals, triple integrals, how to solve those, and then different applications of those concepts. So a lot of the things that we see moving forward are going to be things that you have seen in Calculus BC, Calculus AB, 2-dimensional calculus, but now those same ideas expanded into 3 dimensions or more, depending on the situation. Okay, so when we talk about functions of several variables, for the most part, we are going to be talking about a function of x and y. So for example, when we had like y is equal to x squared, that would be a function of x. Well, now we're going to have like f of xy is equal to x squared plus y squared. So we have a function of x and y. So you can sort of treat that f of xy as your z when we talk about these things, and we're thinking about this in a 3-dimensional setting. Okay, so the first thing we need to talk about is the domain. So when we specify a domain in a multivariable situation, we're going to be specifying the values for all of the independent variables. So all possible values for the independent variables. So typically the x and the y. And then when we talk about the range, obviously that would be talking about the values of the function itself. Okay, so when we have a function of several variables, then essentially what we'll be talking about from a domain standpoint, if we want to talk about the domain, then we can say basically that all of the values of x and y that are defined for us, that would be the domain of my function. And we can graph, obviously, the domain, and we can graph the range as well. Okay, so let's take a look at an example here. It says, let f of xy equal the square root of y plus 1 plus the natural log of x squared minus y. Find f evaluated at e0 and sketch the natural domain of f. Notice that the domain is found by using the restrictions implied by the square root function and the natural log function. Okay, so it's pretty much self-explanatory here in terms of how are we going to figure out domain. Same thing that we would have done when we were working with 2-dimensional calculus. We would look at things here from the standpoint of, okay, with the square root, what's possible in my square root? I can have anything from 0 and above in my square root. So from that, I can see for my domain, I know that y plus 1 has to be greater than or equal to 0. And that means y has to be greater than or equal to negative 1. In addition to that, with the natural log, I know that the argument for a natural log has to be greater than 0. Well, that means x squared minus y has to be greater than 0. That means y has to be less than x squared if you solve that inequality. Okay, and so the domain is already graphed below. So this goes back to stuff that if you think back to Algebra 2 and Pre-Cal, when you would graph the solutions to systems, this is sort of that same idea. So we have a system of inequalities, y greater than or equal to negative 1, and then y less than x squared, and it's everything between those two because they both have to be true at the same time. Okay, also, with the notation, they said to evaluate f of E0. So that means I'm going to plug in E for X, and I'm going to plug in 0 for Y. So just as you would expect, and in this case, that would be the square root of 0 plus 1 plus the natural log of E squared minus 0. And that would be the same as 1 plus 2 natural log of e. Natural log of e is just 1, so we're going to end up with 3. Okay, so some of that's just notation. Some of it's just the idea of getting accustomed to the domain restrictions that we were talking about earlier. All right, so let's take a look at another example. Now, this is a little more complicated because we have a function of 3 variables. F of x, y, and z is equal to the square root of 1 minus x squared minus y squared minus z squared. It also says to find f of 0, 1/2, negative 1/2. Okay, so we want to find both of these things. So first of all, let's just find this function value. F of 0, 1/2, negative 1/2. We always go in alphabetical order. So the 0 will be plugged in for the x, the 1/2 will be plugged in for the y, and the negative 1/2 would be plugged in for the z. So this would just be the square root of 1 minus 0 minus 1/4 minus 1/4, which is just the square root of 1/2. Or you can write that as root 2 over 2. Square root of 1/2 would be perfectly fine as a solution, but if you want to simplify it, you can. Okay, so now let's talk about the domain. So for the domain, it's a little different this time because we've got 3 variables in here, but we still are going to use our same, common understandings of things like square root functions in this case. We know that the radicand, the value inside the square root, has to be greater than or equal to 0. So 1 minus x squared minus y squared minus z squared would have to be greater than or equal to 0. Well, if I rewrite that in a slightly, different way, I can move the x, the y, and the z terms over to the right side, and I'll get x squared plus y squared plus z squared would be less than or equal to 1. So think about what that domain actually is. And so what we have there is the equation of a sphere. And so our domain would be all values inside that sphere that's centered at the origin with a radius of 1 and on the surface of the sphere because it's less than or equal to 1. So that includes the surface of the sphere. Okay, so that's how we define our domain. It's not really difficult to do, but you just have to get accustomed to the fact that we're dealing with more than just like we were before, like just an x. Now we have an x and a y typically, or we can have, like we saw on this one, an x, a y, and a z, and we can expand that to as many variables as we need to. Now, when we graph these 3-dimensional functions or multi-variable functions, it can get pretty complicated in terms of actually sketching these things out. And we've seen that over the course of the last couple of months. So what we do a lot of times is we graph what are called the level curves of a function. And what we create is essentially like a topographical map of what the function would look like. So for example, it says describe the level curves of f of x, y is equal to x squared plus y squared. Well, what we're going to do is we're going to define different values to represent, in this case, the left side of the function. So for example, we would say like k is equal to x squared plus y squared for my level curves. Well, let's let k equal 1. And if we let k equal 1, that means we have x squared plus y squared is equal to 1. And everybody knows what that looks like. That would be a circle with a radius of 1 centered at the origin. Or we could say k is equal to 2. If we did k is equal to 2, again, we'd have x squared plus y squared is equal to 2. And that would give me a circle with the center at the origin with a radius of the square root of 2. So in the end, what we're creating there are concentric circles. So if I wanted to here and I wanted to sketch what this looks like, I can sketch these level curves. And this is giving me sort of like an overhead view of what this figure looks like. So I'm just going to put a few points on here on my graph so I can measure this off somewhat accurately. And if I have a radius of 1, I know I'm going to go through all of these points. So that would be one of my level curves. We did another one where we went to k is equal to 2. We have a square root of 2, which is around 1.4. So again, kind of the same idea. I know I've got my circle going through these points, and we're creating these concentric circles. Okay, so in the end, we kind of know what this figure is going to look like, right? We've got a paraboloid here, but what we're doing, we're essentially looking at the paraboloid from above, and we're looking at it for different defined z values from that above overhead view. Okay, so same idea. Let's look at this next one. So we have f of xy is equal to x squared minus y squared. Well, essentially, we would say k is equal to x squared minus y squared. So we could do, for example, 1 is equal to x squared minus y squared. That would be when k is equal to 1. And so that's a figure you should recognize. That would be a hyperbola. And then we can do the same thing with k is equal to 2. We could have 2 is equal to x squared minus y squared. And to get that one more in our, sort of standard form, that would be 1 is equal to x squared over 2 minus y squared over 2. Okay, so we've got these hyperbolas if we look at it from the overhead view this time. So I'm not going to sketch that one, but you could easily sketch those hyperbolas if you wanted to, and that would give you a view of what those level curves look like. Okay, so let's take a look at creating some basic graphs. Now, I'm not going to ask you to graph a lot of these things three-dimensionally because it's very difficult to do. But when you have things like planes, or you have things like hemispheres, or you have things like cones, those are things that I would expect you to be able to sketch. When we get to the more irregularly shaped functions, I'm not going to ask you to graph those things out by hand. But this problem, it says the graph of the function f of xy is equal to 6 minus 3x minus 2y. It's shown below. So how can this graph be easily created? Well, you sort of have a hint here, right? First of all, this is the equation of a plane. So the way we're thinking of this is sort of like z is equal to 6 minus 3x minus 2y, right? So f of xy is like our z. So if I want to create this graph like I've shown here, I know I have the equation of a plane, but to have a reference to where that plane is located, it's nice to have it sort of fixed to these axes like we've done here. So what we can do is we can say, okay, if we want to know where we are on the x-axis, we just say y is 0, z is 0, and that gives me x is equal to 2. I could do the same thing with the y value, for example. I could say x is 0 and z is 0. And that would give me y is equal to 3. Same thing if I want that z value. I could set x equal to 0. I could set y equal to 0. And that's going to give me z is equal to 6. So from that, now even though I'm graphing three-dimensionally, I can at least plot those 3 points. And if I just connect them together, even though it just sort of looks like a triangle, knowing that this function has a domain that extends forever in the x, the y, and the z directions, or in terms of those values, that means that's where my plane is, and then I can just imagine it being extended out. So we do have a way that we can plot these somewhat accurately when they're more basic type of figures. Okay, so here's another example of just looking at these graphs. It says, in each part, describe the graph of the function in an XYZ coordinate system. Okay, so what they would give you on a problem like this is just this, without the figure that I have to the right. But we can easily create the graph of the figure, just like we did on the previous one. This is the equation of a plane. And with this plane, then we can easily, say where it's located in terms of the z-axis intercept, the x-axis intercept, and the y-axis intercept. And now I've got the equation of a plane, and I also have a way to reference where it is in space. Okay, the next one here, B, it says f of xy is equal to the square root of 1 minus x squared minus y squared. Well, remember, this is sort of like z equals the square root of 1 minus x squared minus y squared. Let's get rid of that square root, and this becomes x squared plus y squared plus z squared is equal to 1. Well, that looks like the equation of a sphere, but we have to account for the fact that if we solved for z again, we would get a plus or minus. You can see here, we've only got the positive square root, so we're just looking at the top half of the sphere. So if I wanted to describe this, I could say it's a hemisphere with a radius of 1 centered at the origin with its base in the xy plane. Okay, so pretty simple to describe and also pretty easy to figure out what it's going to look like just by using some of the common figures that we've seen before. All right, so here's another example. We've got f of xy is equal to negative square root of x squared plus y squared. And again, if you're not sure what it looks like, if you're not given the graph like we have here, we can always just start with our z and then solve for the more standard forms that we saw of these things as we were working through all of the different types of surfaces and figures that we've looked at throughout the course of the year so far. So I can square both sides again, and in the end here I'd have z squared minus x squared minus y squared is equal to 0, and you can see we've got a cone here. So if I were to describe this, I would say we have a cone with its vertex at the origin opening down. You could get more specific than that and talk about the slopes. For example, in the zx direction, the zy direction, you could get specific with that if you wanted, but the main thing would be just say it's a cone with its vertex at the origin opening down. Okay, so not really that difficult to do. The biggest thing about when you work through the assignment here, the biggest thing is going to be getting accustomed to seeing these functions in terms of several variables. Okay, so the last thing that I want to talk about here is what we call a contour map, also sometimes referred to as a topographical map. So when we talk about a contour map, essentially what we're doing is we're looking at those level curves from above. So remember on that problem a little bit earlier, I sketched out these level curves. And essentially what we were doing was looking at the paraboloid from above. Well, that's what a contour map is. So for example, let's say I've got this view. It says this is the perspective view of a model hill with 2 gullies. So when I look at that from above, you can see that these concentric figures are representing sort of different altitudes on that hill, or different elevations of that hill. And each one of those concentric figures is representing going up in 1 unit, or one, in this case, 1 represents 100 feet. So we're at 0 feet, 100 feet, 200 feet, 300 feet, and so on. So once you understand how to read these things, you can start to get a feel for what the 3-dimensional figure actually looks like, and you can just plot it in 2D. So this is really commonly used in things like when you're outdoors and you're hiking, or like for me, mountain climbing. Looking at a topographical map is something that you can do and get a feel for what the terrain actually looks like, and sort of plot your course based on how you want to approach this. Do you want to have a really steep ascent to the top of this thing? Do you want to take a really sort of easy, simpler route? And, by looking at those contour maps, you can figure that out. Okay, so let's take a look at one that's a little more complicated. We have a contour map for a function shown below, and it says use it to estimate f of 1, 3 and f of 4, 5. Okay, so remember, we're essentially saying that we've got a function of x and y, and what we're looking at here is a contour map, so it's showing us the z values, but from an overhead view. So if I want to figure out what is f of 1, 3, what I've got to do is I've got to go onto this map that I have here, this contour map, and go to the point 1, 3, and you can see it's around right here. Well, I know that when I'm at the point, or excuse me, I went to 3, 1. Let's go to 1, 3. When I'm at the point 1, 3, I'm around right here. And you can see I'm between 70 and 80. And it looks like I'm closer to 70, so I'm going to say that's roughly, 71 or 72. I'll just say 72. All right, let's look at another point here, 4, 5. So if we're at the point 4, 5. So if we're at the point 4, 5, let me put my coordinate on the graph. Looks like we're about right here. And you can see we're roughly somewhere between 50 and 60, because I've got this curve that's representing 50. I've got this curve inside of it that's representing 60. So I know I'm closer to 60 than I am to 50. So I'm going to say this is roughly, about 58. So we can get a pretty good feel for what the z value is based on those contours. So as long as we know what each contour is representing, then that gives us a feel for it. And that's why when I created my contour map over here, I labeled, k is equal to 1, k is equal to 2, and so on, because those are my different z values. So if I really wanted to be specific on this thing, I could label each concentric circle, k equals 1, k equals 2. And then I know, okay, this is what happens when the z-value is 1, the z-value is 2, and so on. All right, so that's the majority of what you're going to do in this assignment. I did include, just so you could see, this is actually a picture of a topographical map of Denali. And I think most of you guys know I climbed Denali last summer, so it was about almost a year and a half ago now. But in terms of the route that we took, if you follow along on the route here, you can see topographically the route that we took. And so a lot of things that we try to do when we climb a mountain is we try to find sort of the path of least resistance. And if you trace along this path that's on this map, you will notice in a lot of places, and in fact in the majority of the places where we ascended up the mountain, we were going up in places where those contour lines are really far apart, because we're trying to take the easiest path to the top. Now, obviously, there are some sections where we went up some really steep parts, because sometimes it's unavoidable to get from one area to the next, but it gives you a feel for what the terrain is that you're going to encounter just by being able to read how those maps are constructed.